So basically what happens is when you have cos equations, that is x equals to x naught cos omega t, your v becomes minus omega x naught sin omega t, and your acceleration becomes minus omega x naught square cos omega t. Agree?
Yes, ma'am.
Isn't it?
Yes, ma'am.
Because when you do dx over dt, you will get this. When you do d square x over dt square, you will get acceleration. Done?
Yes,
Similarly, here also I am having the equation x equals to x naught sin omega t. V equals to omega x naught cos omega t. Similarly, acceleration will be minus omega square x naught sin omega t. Okay. Done?
Yes, ma'am. Yes, ma'am.
Okay. Also, we had studied that velocity is nothing but given by omega under root x naught square minus x square, and acceleration is given as minus omega square x. Correct?
Yes, ma'am.
Okay. Now, after this topic, let's start the new one, and that is energy transfer. Energy we had done or not?
Energy transfer. Once again, I'm just checking.
Just check.
Presentation, potential, kinetic. Yes, ma'am. We have done that.
Okay. So,
Okay.
and the graphical representation of kinetic energy and potential energy is also done?
Yes, ma'am. Yeah. Yeah.
Okay. So, now phase difference is remaining, or is it done?
I think we were doing phase difference. We were
doing phase difference.
Ending with the phase difference. Lastly, I wrote 0 pi by 2 pi, 3 pi by 2, 2 pi.
Okay. So, phase difference we were doing, right?
Yes, ma'am.
Okay. So, this chapter is over and we have to start C2 chapter, and that is wave model. In wave model, we are having the very first topic as waves. Okay. Waves is nothing but, just check, no? I guess we have discussed this topic also.
Yeah, ma'am. Basics, I think we did like the basics.
Tell me, what was the last topic that we have sorted?
You drew a graph, ma'am. You drew a graph about the, what do I say? The pies, like the phase difference. You drew a graph for the phase difference.
Okay. So we had discussed reflection, refraction, diffraction, everything we had discussed, right?
Yes, ma'am.
And after that, interference pattern?
I don't remember interference part. I remember till the diffraction part.
Okay. So let's start with that.
Yes, ma'am.
And here we are having the next topic, and that is interference. Just check what is interference. So basically, interference is defined as when two waves cross each other, they can add together, or even they create an extra big wave. Okay. Extra big wave they create, or even they cancel out.
Yes.
Okay. So why does it happen and how does it happen? Suppose we are having wave A, which is traveling like this. We are having wave B, which is traveling like this. So here you can see that your wave B is in phase with A, correct?
Yes, ma'am.
So the resultant will be addition of the two. So this will be 2A if this is A and this is A. Okay, understood?
Yes, ma'am.
Okay, now this is known as interference. Okay, any doubts?
No, ma'am. And if they are going like upward and downward, they cancel out, right?
Yeah. And this is known as constructive interference. This is possible when you are having path difference of lambda, 2 lambda, 3 lambda, and like that. Whereas if suppose I have one wave to be traveling like this, okay, that is wave A obviously. If I have wave B, which is traveling like this, okay, so
Yes,
what
ma'am.
will happen? Here it is in the negative cycle, it is in the positive cycle. So the
Zero.
resultant will be a straight line, which will be known as destructive interference pattern. Here, the path difference is pi by 2, 3 pi by 2, 5 pi by 2, etc. Done?
Yes, ma'am.
Any doubts?
No, ma'am.
Here, the phase difference is lambda pi, 2 pi, 3 pi, and so on. That is n pi, where n is your whole number. Okay?
Yes.
Okay. After this, here, the phase difference is n plus half pi. Or even you can say that it is pi by 2, 3 pi by 2, 5 pi by 2, like that. Okay? So it goes like that in destructive interference. Then after this, we are having next topic, wave pulse in a string. So what do we understand by wave pulse? First of all, pulses occur only in the standing wave. In standing wave, no energy transfers. Suppose here the A and the B point are fixed. I had provided a tension from this end, that is the origin. So it will be traveling towards this side, and after some time it will be seen as coming back. So this is the reflected wave, this is the incident wave, correct? And
Yes, ma'am.
if suppose they both meet, they will be creating a node like this. Making sense?
Yes, ma'am.
Okay, so this is standing wave. The properties are it should be released from a coherent source.
Like the guitar.
Second is here the energy transfer is not possible. Third one is here they always come from the opposite directions. That is, one will be incident, second one will be reflected. Making sense?
Yes, ma'am.
The speed with which they are traveling is represented as v. Okay. And after that, they superimpose each other. And here we can see the superposition pattern. Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
So here the v is given as f lambda, obviously. Okay.
Yes, ma'am.
Done. And here, if you observe very carefully, then a continuous wave which is moving along the string. Okay. And from the position at rest, it starts going, which is relative to the string. Then also we will notice that the time between one peak passing and the next peak is t.
Yes, ma'am.
One peak passing and one peak coming back. The time between them is capital T.
Yes, ma'am.
Okay. Because one is constructive wave, then the second one will be destructive. So the between distance will be capital T. Okay.
Yes, ma'am.
Okay. And the distance traveled will be equal to the wavelength then. Okay. So the
Yes.
velocity can be written as distance over time, hence wavelength over time. Clear?
Yes, ma'am.
Also it is v equals to f lambda. Let's do one question over here. Here is the question. Calculate the wave velocity of a tsunami with time period 30 minutes and wavelength 500 kilometers. Always remember that your unit should be meter per second, hertz and meters. Okay.
Yes, ma'am.
So basically 30 minutes
30
is,
into 60.
yeah, 180 seconds. Done. After this, your distance is how much kilometers? 500.
500 into.
Done. After that, we have to find the frequency. What we have to calculate? Wavelength.
Yes, ma'am.
Velocity, sorry. Velocity we have to calculate. So,
Lambda.
the velocity will be v equals to distance over time. So, that will be 5 into 10 raised to 5 over 180. You will get the answer. Let's do the second one. Two strings are joined together as shown in the figure on the left. If the wave velocity, let me give you the figure also now.
Yes.
Okay. So two strings are joined together as shown in the figure. If the wave velocity in the thin string is twice its velocity in the thick string, calculate the wavelength when it gets into the thick string. Yes. So when it gets into the thick string, what will happen?
If it gets into the thick string, then the wave calculate when it gets, then it will be subtracted
Subtracted.
Is twice its velocity in the thick string. It's twice.
Okay.
The
Okay.
thicker string is it more, ma'am? Is it? Yeah, they say it is twice. So twice minus like how I am imagining the question to be is there will be the other wave which is twice the length, and this
Okay.
is the shorter one. So the resultant would be the one which is subtracted some.
Okay, let me tell you. So basically, two strings are joined together and they are shown in the figure that the wave velocity in the thin string is twice the velocity in the thick string.
Yes, ma'am. So it will get decreased, like the length, total length will be.
Is it like that? V
Yes,
equals to F lambda.
yes,
Calculate the wavelength when it gets into thick string. So when it gets into thick string, that is 0.4 meter, it will become 0.2
yes, ma'am. Yes, ma'am.
because it
Yes,
will be 0.4 half,
yes, ma'am.
right?
Yes, ma'am.
Let's go for the next. When the wave meets the knot, part of it will be reflected. Explain whether the reflected wave will be inverted or not. Yes. Will it be
Yes,
inverted?
wave meets the knot. Wave meets the knot.
Hmm.
We reflected. Part of it will be reflected. Explain whether the reflected wave will be inverted or not. Inverted in the sense it is upside down, right, ma'am?
Yeah. Obviously, reflected wave will be upside down, no?
Yes, ma'am. Yes, ma'am.
This is an incident and this is reflected. So why
Yeah.
you are taking so much of time? This will be inverted. If y is the amplitude of the wave in thick string will be smaller in the thin string comparison to the thin string. Yes.
Why is the amplitude of the wave in the thick string smaller than in the thin string?
Hmm.
Amplitude is shorter. Yes.
What?
Smaller. Amplitude is smaller.
Basically, what happens here is when the wave is reflected, so the energy in the transmitted wave becomes less.
Yes, ma'am.
Okay. Whenever the wave is reflected back, so the energy in the transmitted wave is less and hence it will be
Smaller.
smaller. Okay. Because
Yes.
energy is nothing but intensity and intensity is directly proportional to amplitude square. Done?
Yes, ma'am.
Okay. I'm just giving you 1 minute of the time. Solve question 3. Be quick.
The end of a string is moved up and down with the time period 0.5 seconds. If the wavelength of the wave is 0.6 meter, what is the velocity of the wave? It is 0.65. The velocity is 1.2 meter per second.
Velocity is how much?
1.2.
Let me check. Yes, 1.2 is correct. So let's move for the next part now. And that is the graphical representation of the transverse wave. Okay.
Yes, ma'am.
Let's start with that. Okay, now check this diagram. Yes, tell me. What's the issue?
It's transverse.
Transverse wave.
Okay, ma'am.
You know what is transverse wave?
Yeah. 1 second, ma'am. I'm trying to.
No.
Transverse wave is when both waves.
No, you are wrong. Let me explain. When a wave is traveling, basically, the particles
Are moving.
that are forming a wave basically vibrate. So some of the particles vibrate like this, some particles vibrate like this. Suppose my propagation direction is like this. Okay.
Yes, ma'am.
And here we are having the particles.
Like in the ocean, if the
Yeah. So when the motion of the particles is perpendicular to the energy transmission, it is perpendicular, it is transverse wave. Like your light wave, all the spectrum wave, EM wave are transverse wave. Whereas when the particles which are forming the wave, they vibrate like this, parallel to the propagation direction. Okay, they will be known as longitudinal wave.
Yes,
Here it is transverse wave.
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So now here there are two ways we can represent a wave graphically by drawing the displacement time graph, okay, or displacement position graph. Done? So
Yes, ma'am.
basically, suppose here we are having 2 points A and B of the transverse wave. Point A is moving up and down with a simple harmonic motion, okay, and at present it is at its maximum negative displacement, correct? Whereas as the wave progress and past the E point, the wave will be moving up and then it will be moving down, correct?
Yes, ma'am.
After A point, when it goes further, it will be going to go up and then after it will come down. Done? So we
Yes,
can
ma'am.
also draw the graph for the point B. This point B starts with 0. Okay, so how it will be drawn further?
Up, down,
I'm giving you the diagrams. Check here. So this is A point and it had reached here. Next it will be reaching here. Correct?
Yes, ma'am.
Okay. So this is the graph which will be obtained. Correct?
Yes, ma'am.
Okay.
Down.
And again, it's position time graph if you want to draw, or if you want to draw the displacement time graph, it will be drawn something like this. Displacement time graph. Check. So it will be like this. Between two crest or two graph, it will be lambda. A point is here. So now it will go up. So here it came up. Okay. And this is the amplitude of the wave. Then after that, it will go down. Similarly for B point, it will go down first, then it will go up. Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Now, next part. The equation of wave. Okay. Can you write for me the equation of wave?
Yes, ma'am.
Okay, do it. Be quick. Tell me the equation of wave.
1 second, ma'am. Can I check the data booklet? Can
Sorry?
I use the data booklet, ma'am?
Yeah, sure.
The one with x naught
Okay.
sine wt plus phase
Say it again.
x naught sine wt plus phase difference.
Okay. A general wave is like this. Correct?
Yes, ma'am.
Okay. Now let's calculate with the phase difference also. Check here. Okay. So here position is sine omega t 0. Theta is
Yes, ma'am.
0. So sine omega t is also 0. Amplitude will become also 0. Correct?
Yes, ma'am.
It had reached here. So pi angle it had traveled. So omega t minus pi. Now it had traveled here. So pi more distance it had traveled. So omega t minus 2 pi. Any doubts?
No, ma'am.
Are you sure?
Yes, ma'am.
Now after this, let's come back to the next pointer. And that is okay. So the next pointer is waves in the slinky.
Yes, ma'am.
Obviously slinky it is, so it will be a longitudinal wave.
Yes, ma'am.
Okay. Listen here very carefully. First, let me show you a longitudinal wave. Check. This is a longitudinal wave. Compression, rarefaction, compression. Sound wave is always a longitudinal wave. Okay. This
Yes,
is
ma'am.
the direction of the disturbance from one compression center to another compression center will be the wavelength. Okay. These
Yes,
are
ma'am.
the two crests. Center of this, crest point, two crest point. Okay. Wave
Okay,
direction
ma'am.
is in this direction. One crest to crest distance is always lambda. Any doubts?
No, ma'am.
Let me show you the reflected wave for this now. The same wave.
Yes, ma'am.
Okay. Check. This is the reflected wave of this. The wave had traveled towards this side. When it bounces back here, you will observe some of the rarefactions, then compression, then rarefaction, and then compression. Easy?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay. Because here it was compression, so when it is bouncing back, you will receive first the rarefaction and then compression, then rarefaction, and then the compression. Okay?
Yes, ma'am.
Okay. Now for this, we have displacement time graph. Check the displacement time graph for this. Check how is it done. Here it is rarefaction. Here you can see the compression in these
Yes,
three
ma'am.
bubbles.
Yes, ma'am.
Okay,
Yes, ma'am.
done. So just check the spring. Same thing is given. Compression, rarefaction, and this. Here they are close enough, the springs. Here they are apart enough. Here again they are close. Here you will see the far enough. Again they had got close. Again they have got far enough. Done.
Yes, ma'am.
Check the graph for this now. Check the graph.
Yes, ma'am.
Just for ball 1, this will be the graph. Ball 7, this one. This will be the graph. Can you identify how and why?
First, there is 1 second, ma'am. First, in this, the first part, there is how and why. It looks the same.
What?
Ball 1 and ball 7 both look the same, except like the first one is the second one is like a what do I say this? The second graph I feel is a continued part of the first graph.
Yes. You just have to compare these springs in between with this graph.
Okay, ma'am.
Hmm.
They both start at 0 and then this.
Listen, leave this one upper line. Just go to the below line. Listen very carefully. Just go for the below line. These balls are nearby to each other, whereas these are apart and these 4 are apart. Correct?
Yes, ma'am.
So when they are apart, they will be forming crest and trough. When they are nearby, they will be at 0. Clear?
1 second, ma'am. If they are at near, if the ball is at near, they will be 0. Okay, ma'am.
Okay. Any
Yeah.
doubts?
I'm just analyzing the graph, ma'am.
Okay.
Just give me a second.
Okay.
Yes, ma'am.
Are you done?
Yes, ma'am.
Okay now. So after this, we are having sound wave. Let me show you how does the sound wave actually travel. So sound wave basically travel like this. Check. Compression, rarefaction, compression, rarefaction, compression, rarefaction like this. Okay.
Yes, ma'am.
Am I making sense here?
Yes, ma'am.
Okay. So sound basically is an example of longitudinal wave, but okay. And when the body moves through the air, it compresses the air.
Yes, ma'am.
Okay. And the air basically expands and it compresses the next layer of the air, which passes the disturbance from one layer to the next.
Yes,
So
ma'am.
we can compare it to the oscillations also,
Yes,
where
ma'am.
a continuous wave is propagating through the air. Okay. And it's transferring the energy from one point to another point, which is now known as sound wave.
Yes, ma'am.
Clear?
Yes, ma'am.
Okay. After this, let's come to the transverse wave. First, let me show you the mechanism of your sound wave. How does the air helps out? If you are having warm air, will be traveling like this. Okay. How does the warm air goes? Warm air is always found in the upper altitude, whereas cold air stays at the lower altitude. Correct?
Hello, ma'am.
Yeah.
Yes, ma'am. I just rejoined. I'm not sure how I left, but I just rejoined.
It's okay. Check the diagrams and just compare it with your understandings.
Yes, ma'am. This is like the air, and the other this sound is happening in like the warm air versus the cold air, ma'am. The second diagram.
In the second diagram, warm air is always found in the higher altitudes and the cold air is found in the lower altitudes because
Yes,
of the denser thing. Cold air is more denser than the warm air. Hence, the wave will be, the propagation of the sound wave will be traveling like this. Whereas in the cold air, it will be traveling like this.
yes, ma'am.
Okay. Any doubts?
No, ma'am.
Okay. Now, after this was all about longitudinal wave. Now, let me show you the transverse wave. Check this. These are the wavelengths and frequency of the waves.
Yes, ma'am.
Clear, no?
Yes, ma'am.
Okay. So basically, gamma wave has the highest frequency, so lowest wavelength. If I talk about radio waves, so it will be having highest wavelength and smaller frequency. Done. Here we can see the visible range, which is from 400 nanometer to 700 nanometer. The wavelength of red light is 700 and the wavelength of blue light, indigo blue, is 400 nanometer. Clear?
Yes, ma'am.
Okay. So there are different wavelengths which we are finding in the visible light, okay, and they have different colors also. However, what happens is our perception of color is not so simple. For example, red light when mixed with the green light, it becomes yellow, and the velocity of light in a vacuum is approximately 3 into 10 raised to 8. So you will apply the formula and you can see that the brightness is directly proportional to the intensity of the wave. Hence, your intensity is directly proportional to the amplitude square. Okay, it is always measured in watt per meter square, that is power per unit area. Okay.
Yes, ma'am.
So the light intensity is measured in the meters. As you move from one point to the light source, its intensity gets a little less, and it is because the light spreads out, so the power per unit area is reduced. Done?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So the formula for the intensity is also written as power per unit area, so 4 pi r square. Clear?
Yes, ma'am.
Okay. Now let's have a look on the next. Shall we solve one of the question?
Yes, ma'am.
Okay. But you will do it fast. Okay.
Okay, ma'am.
Okay. Do it.
Yes, ma'am. This is a longitudinal wave. Like this is a uh,
Sorry?
this is a wave which is like 90-degree perpendicular. So this is longitudinal.
Yes, it is. Next.
Using data from the diagram reduced from the song wave and the
Solve 3 of them and then give the answer.
Okay. And lambda is 110
How much
meters.
is lambda?
10.
No, it is 0.5 meters.
The
Check it
wavelength,
again.
the wavelength, ma'am, the wavelength.
Wavelength is 0.5.
Okay, ma'am.
Can you do it fast?
10, 11, 12, 13, crest to crest. 10.
Okay.
Once again, I'm doing the last question first. Just give me a second, ma'am.
Last question. It's asking about that. What is the speed? Speed equals to V equals to F lambda.
330.
Isn't it? F is given as 660. 660, right?
Yes, ma'am.
Okay. And what is the wavelength? 0.5.
Ma'am, but here it is in mm, right?
Yeah,
That
so
is,
you need to convert it.
yes, ma'am.
So it will be 330 meter per second. Okay.
Yes, ma'am.
Done.
So it will be
Okay.
0.0005 if I convert it. 0.0005.
660 multiply 0.5.
Yes, ma'am, but you said I have to convert the mm to m. So I have to make it more decimal.
It's already in meters what you are converting.
No, ma'am, it is in millimeter.
Bache, that is amplitude. You have to calculate wavelength. Wavelength 0.5 meter is the answer.
Okay, ma'am.
Okay.
Yes, ma'am.
Yeah. Let's move for the next part now. And that is, any doubts still here?
No, ma'am.
Okay, let's move for the next, and that is wave phenomena. So in wave phenomena, we have certain topics. First is like wave fronts. Just have a look over here. Suppose this is my water. Here I had thrown the stone. So it will create a wave around it in concentric circles. Right?
Yes, ma'am.
Okay. And when you will draw it, it will be something like this. Correct?
Yes, ma'am.
Everywhere you will be able to find.
When we throw like, for example, this also forms if we throw a stone in the lake or something, ma'am.
Hmm?
If we throw a stone in the lake,
Hmm.
what kind of wave does the resultant one will form? If
What kind of wave?
yeah,
It will be a
there will be like this thing
transverse wave. It is.
like it will be like this and this, something like that. If we throw a stone like in a from a very long distance, and then if we throw it in the water, we'll have some kind of a reaction like that.
Okay, just give me a sec.
Yes.
Let me just. They are the combination of both longitudinal as well as transverse.
Okay, ma'am.
Because they go up and down also, which basically is a transverse wave doing. And they
Yes.
also move in the forward and backward direction, which is a longitudinal wave now.
Yes, ma'am.
Okay, so it's a combo of both. Anything else?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Fine. So shall I do the draw the waves now? Can you see the
Yes.
screen? So it's creating a crest. Done. Now, this, and this point all are at 90 degree. This point all are at minus 90 degree. So all these points which are in one phase will be known as wave fronts. Understood?
Yes, ma'am.
Any doubts? You want to ask something?
No, ma'am. No, ma'am.
Sure?
Yes, ma'am.
Okay, let me give you a picture of that. So here is the picture. Okay. Can you see? So the definition will be the point sources that produce circular wavefronts. Okay. Or in fact, the wavefronts are defined as the circles that we see, which are actually the peaks or the troughs of the wave. We call them as wavefronts. Okay. And a wavefront is basically a line which joins the point that are in phase. Okay.
Yes, ma'am.
Understood?
Yes,
So
ma'am.
like here I am getting so like here, check. This is one line. So all the points which are coming over it, all the points which are coming over it will be a wavefront. Okay.
Yes,
And
ma'am.
it is defined as the circles that, not the circles exactly, but the wavefront is any line which is joining the points that are in phase. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Akshata, am I making sense to you for this?
Yes, ma'am. Yes, ma'am.
Okay. Now, after the wavefronts point, we have the Huygens construction and the Huygens propagation. Okay. Now, we think that the wavefront has been made up of infinite number of new centers of disturbance. Okay. See here.
Yes, ma'am.
One disturbance is like this. This is the second disturbance. Third disturbance. Fourth disturbance. So, like this. Okay. So
Yes,
whenever you are drawing any ray like this, they all are connecting. What the hell is happening here? So whenever I am connecting all the points in one phase, because see here is a circular region, so it will come up. This thorough line will come up. Are you getting?
Yes, ma'am.
Okay. So therefore, this thorough line will be consisting of points that will be known as wave fronts because they are making one pattern.
Yes, ma'am.
Done? Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. So this is it for the day. Okay. Let's meet again tomorrow. Done? Bye.
Bye, ma'am. Thank you, ma'am.
Bye.